Good afternoon, calculus students. So it's Mr. Chan again. So how are you guys doing? And today I would like to talk about that sections 9.3 convergent test for series with positive term. So this one is about the integral test. So if f is positive, continuous, and it's also decreasing. Okay, so this one just fill in the blank. So this one is just a precise definition of the integral test. For x is greater than or equal to 1, and f of this one, let's say that f of n equals a sub n. For n is greater than or equal to 1, then sigma a sub n from n equals 1 to infinity, and the integrals of f of x dx from 1 to infinity, either both converge or both diverge. So basically what this one is saying that if the integral of f of x, because f of x is kind of like f of n here, so let's say that the integral can be founded with the finite number, so let's say that equals n, so that means the sum, the series, would be considered convergent. Okay, so let's say that if the integral, so the sum is going to be infinity, that means the series is going to be considered divergent. Okay, so now let's find out what's happening here. So determine if the integral test apply to sigma 3 over x squared plus 1. This one's supposed to be n squared. So this one's supposed to be given as n squared. So let's set up the function first. So let's say that the function would be considered f of x. So that equals 3 over x squared plus 1. So again, three conditions that we need to satisfy. So the function got to be positive, continuous, and it's decreasing. So try to sketch the graph here. So this one, it's kind of like a bell curve shape. So anything that x is greater than or equal to 1. So for this part right here, so you can see that the function is continuous. It's positive because that's right above the x-axis. And also it's decreasing. So another thing to find out whether that's continuous and also decreasing, you can use that the first derivative test. But instead of doing that, just make the graph. It's just basically you can visualize what's happening here. So if this one is the case, so we're going to use that the integral test. So this one, it goes all the way from 1 to infinity. And then f of x, which is 3 over x squared plus 1 times dx. And then one thing that we notice, so this one is called the improper integral. So improper integral, so integrated first. So we do have limit as b goes to infinity. So this one basically integrated. So we do have 3 times arctangent or inverse of tangent of x. And this one runs all the way from 1 to infinity. So using that, the part 2 of FTC, so we do have 3 times the limit. So b goes to infinity. So arctan of b minus arctan of 1. So one thing that we notice, so arctangent of 1, it's pi over 4, because tangent of pi over 4 is 1. And then arctangent of b, so plug in infinity. So if you recognize the inverse of tangent, so it's like a sideways cubic curve. So if b goes to infinity, so arctangent of infinity, so this one is getting close to pi over 2. So it's pi over 2 minus pi over 4 times 3. So we do know that the limit is going to be a finite number. So pi over 2 minus pi over 4 is pi over 4, so 3 pi over 4. So since this one is a finite number, so therefore, and the sum of 3 over n squared plus 1, so the series converges. Okay, so the last statement, so you want to just come up with the conclusion. So since we find that using the integral test, so we come up with a finite number, so therefore sigma n equals 1 to infinity, 3 over n squared plus 1 converges. Since the improper integral has a limit, so we know that the series converges. It may not converge to a number. Okay, so let's just say that a number. However, To approximate the sum of the series, so use the following method, so which means the integral. So from the first term to n it's a natural number, and then we take the limit where n goes to infinity. Okay, so of f of x dx. So use the large value of n and use the calculator to approximate the sum of the series. So we just found it. So the sum of the series, which is considered 3 pi over 4. Okay, so using the same kind of technique. Okay, so now let's see what else that we have for the rest of this. So section 9.3, the continuation, convergent test for a series with positive term. So now we want to try another one. So determine if the integral test apply to this functions. To not this function, it's this series. So let's say that f of x equals 3 to the power of negative x. So this one, well, it's a negative power, so exponential decay. So try to sketch the graph, so it's going this way. So this one is for anything that, well, this one n is greater than or equal to 1. So that means for x is greater than or equal to 1. So as you can see that this one is the decreasing functions. So it's continuous. And also, we do know that the it's positive as well, because that's right above the x-axis. So using the integral test, integral from 1 to infinity, and then f of x, so 3 to the power of negative x dx. Okay, so using that. And this one, again, improper integral. So let's say that limit as b approaches infinity. So the integrals of 3 to the power of negative x, so got to be very careful with this. So we do know that the derivative of 3 to the power of negative x, it's considered, it's like a formula derivative a to the power of x, which is a to the power of x times natural log of a. So the derivative of this one would be negative 3 to the power of negative x times natural log of 3 times negative 1 using the chain rule. But right now it's just the integral. So the integrals of this one, so pretty much it's the exact same thing, 3 to the power of negative x, but divided by natural log of 3. And also don't forget about the negative 1. The negative is not there, so plus, times negative 1. And this one, it goes all the way from 1 to b. Okay, so using that part 2 of FTC, so negative 1, put it out, so limit, and also the natural log of 3, put it out, because that those are the coefficients. And limit b goes to infinity. And what we found here is b 3 to the power of negative b minus 3 to the power of negative 1. So this one is saying that is 3 over infinity minus 1 over 3. So we do know that 3 over infinity, that's 0, minus negative 1/3, it's going to be negative 1/3. And negative times negative is going to be positive, so it's 1 over 3 natural log of 3. And also this one can be written as 1 over natural log of 3 to the power of 3, which is 1 over natural log of 27. So as you can see that this one is a finite number, so the integral converges, so therefore the series converges. So since the integral, again using the definition, so since the integral converges, so therefore the series converges. So then the series, so just rewrite it, the series, which is what, sigma 3 to the power of negative n converges. Okay, so that's the integral test. And now what about the other type of test, convergence of p series? So P series, so this one, so it's called the power series test. So let's say that if you see anything like 1 over n to the power p for the series, so it's like 1 over 1 to the power p, 1 over 2 to the power p, 1 over 3 to the power p. Or this one sometimes can be written as, well, I'll just say that the power, it could be any arbitrary number. So if p it's greater than or equal, it's greater than 1. Okay, so p is greater than 1, so therefore, so the power series converges. Diverges if p it's less than or equal to 1. Okay, so we just need to find out about the power. So determine if that the series 1 over n to the power 5/3 converges or diverges and justify your solution. Well, this one obviously converges because that p it's 5/3. So since p equals 5 over 3, which is greater than 1, by using the P series test, so the series 1 over n to the power 5/3 converges. So it's pretty easy. So for the power series, so anytime that you see the structure is like 1 over n to the power p, so always identifying the power. If p is greater than 1, so that means the series always converges. If p is less than or equal to 1, so the series diverges. Because that when p equals 1, so this one is the harmonic series. So we talked about that before. So to prove the harmonic series diverges, we can use the integral test as well. So let's say that we do have something like 1 over n. Okay, so using that, the integral test. So let f of x equals 1 over x. So the function for that is like this. But this one is for x is greater than or equal to 1. So we're looking at this region here, all the way to infinity. So integrate it, so 1 over x from 1 to infinity. So again, improper integral. So limit as b goes to infinity. So integrals of 1 over x, which is natural log of absolute value of x. And this one, it goes all the way from 1 to b. Plug in that infinity. So natural log of infinity minus natural log of 1. So where natural log of 1 is 0, the natural log of infinity, it's infinity. So it's a non-finite number. So it goes on forever. So since the integral diverges, so therefore the series diverges. Okay, so for the harmonic series proof. Okay, so thank you for watching the first part of 9.3 today. So we're going to continue with that for the comparison test for the second half of 9.3. Once again, thank you for watching it. So I'll see you guys next time. Take care.